Hi everyone, for this question I wanted to reuse a video I recorded in 2020 or 2021, one of those two. So I hope you enjoy it.
Here it is. And the reason why I gave you this one is so we can have two, let me make this a little bigger, two springs, right? We'll pick 50 grams, we'll stop it, and I'm going to assume, just for the sake of this example, that this is the maximum displacement. So I will get the mass right to the line, and then we'll let it oscillate. This is pretty fast, so I'm going to make it slow. Now we're going to drop another mass, so let's say it's double the mass, so 100 grams, right? We'll stop it, and then I'm going to stretch it out to the same distance, right? The same displacement, because that's what it's saying. The example says that when we reached the same amplitude, right, the amplitude, then another mass was added on top of it. So this will help. And then I will release exactly at the same moment when it reaches there. So I think it is very obvious what's happening, right? You guys can clearly see. So now let's see our answer choices. A, the maximum velocity does not change. Well, it is very obvious that it is going slower. B, the amplitude of oscillation decreases. C, the frequency of oscillation, F, does not change. And D, the frequency of oscillations increases. And E, the period of oscillation increases. Okay. So since we have two different springs, that's why it looks like the amplitude is decreased. But that's because we're using the same, two different springs. If we're using the same, the amplitude would remain the same because it was a frictionless surface. So now let's look at frequency and period, right? So we're going to cancel these two. So frequency and period. So period we defined as the time it takes a system, the time a system takes to complete one oscillation, one cycle. And we have the relationship of period and frequency in this way. Period equals 1 divided by the frequency. I'm going to give you another formula for this one, right? This is the period of a system where you have a mass and a spring. It'll be 2 pi times the square root of the mass divided by spring constant. So the period, as you can see, it's not related. Mass is important, right? So something has to change because we're changing the mass. The spring constant is a constant. Pi is pi, 2 is 2. So if we increase the mass, we're going to increase the period, right? And you saw it was going slower. If it's going slower, then the period increases. It takes more time to complete one oscillation, right? So let's say if this is oscillating like that, right? And then we put another mass, so it's harder to move, right? So the period increases. Now, if the period increases, notice how period and frequency are inversely proportional. So if the period increases, that means the frequency has to decrease, right? Don't forget that the frequency is the number of events or cycles per unit time. So if it's taking us more time to do one cycle, then that's going to reduce the number of cycles per unit time, okay? So if we go back to the answer choices, the frequency does change. It decreases. This one says increase, so we cancel A, B, C, D. And the only one left is E. The period of oscillation increases. It takes more time to complete one oscillation. That's it.
Okay, now for question 2 we have The reason that oscillating systems are good to use for clock is, now before we do that, so a clock measures time, right? So we're going to have to deal with time. That means we need to deal with the period of an oscillating system. Let's start with the mass of a spring. And this is for a pendulum. So m is the mass, k is the spring constant, or stiffness of the spring. For the pendulum, L is the length of the string, and g is the acceleration of gravity. And just know that all this should be inside the square root. Notice that oscillating systems, if we look at the answer choices, for instance, let's go from bottom to top. Oscillators are efficient at turning motion into heat. So that's not anywhere related here because we're dealing with time. So that's not the answer. So the frequency of an oscillator does not depend on the strength of the spring. Well, that's K, and of course it does depend on it, right? If you increase the spring constant, you decrease the period. They are inversely proportional. Now, the frequency of the oscillator does not depend on mass. Well, it does for mass on a spring. And I know some of us are thinking, well, mostly we would think of a pendulum for a clock. However, these work too for different types of clocks. So we have to take this one into account. So C is not the answer. Real mass spring systems are frictionless and energy is perfectly conserved. Well, that's not true, of course. So the only one that's left is A. And if you read it, it says the period of an oscillating system does not depend upon amplitude. So neither of these two contain A for amplitude, although after the lab, maybe you saw that. It does affect it a little bit, but we're going to assume these clocks use small oscillations, so these two equations hold true. Therefore, the answer is A, just based on the equation. All right. You have a pendulum built from a mass on a string and want to make it go through a cycle in double the time. What you do is, so let's go back to the equation for the period of a pendulum. All right, so we want to make it go through a cycle in double the time. That means we need to increase the frequency by 2, which if you remember the relationship between frequency and period. So that means we want to decrease the frequency, right, because we want to do double the time. So that means we have to increase the period. So now let's go back to this top equation and see how can we increase the period. Well, we cannot change the acceleration of gravity. 2 pi is 2 pi. So the only thing that we can do is change the length of the string. Many of my students will say, oh, let's just double the length of the string because we want double the time. However, we have to take into account the square root. Because if we were to, let's say, double the length of the string, let's call it T prime. So here we double the length of the string. I'm going to rewrite this equation differently. Mathematically, it'll be the same. And then once again, notice how this part is identical to this one. So then my new period, T prime, is the square root of 2 times my original period. We are not increasing the time by a factor of 2. We are increasing the time by a factor of square root of 2. So that is not 2, of course. Therefore, we need to put a number here that when we do this mathematical process of rewriting this equation, we end up with something that would be equal to 2. And I think you can see it would be 4, right? Because if we quadruple the length of the string, then we would have a 4 here, and we know that the square root of 4 is 2. Let me show the process real quick. So here I have what it looks like when I quadruple the length. Now we can see that T double prime is just like the original period increased by a factor of 2. If you shake the end of a tightened string at 1 cycle per second and then switch to 2 cycles per second. So let's write down a few. No, you know what? I'm going to show you a simulation first, and then we'll deal with some equations. All right. So I like this simulation very much. And I know it says tightened string, so I'm going to use this setup because it's easier to see. So notice I have my frequency at the bottom of the screen at 1 hertz, that is 1 cycle per second, and the amplitude in this case is somewhat irrelevant. I just picked 1 centimeter to make it simple. So then I'm going to start the simulation. Let me go slow motion so I can take a screenshot. And then we'll compare. All right. So now I'm going to pause it and then increase the frequency to 2 hertz, 2 cycles per second. So take a look at the wave, how it looks like. And now let's see what happens when we increase the frequency to 2 hertz. I'll take a screenshot again. And let's compare them. All right, so there we have it. We have both waves right there. You can see the difference. Now let's look at the answer choices. We have the wave travels twice as fast. So before we go on to if this is true or not, I want to give you an equation for the speed of a wave that is not in your textbook. So the one from your textbook says the following: that the speed of a wave, v wave, is equal to lambda f, that is wavelength multiplied by frequency. There's another one that I want you to have because you need to use it for your question work. This is the speed of a wave is equal to the square root of the tension force. This is force of tension. Normally is tension. And this is the Greek letter mu. I know we use that for coefficient of friction, but we ran out of Greek letters. So in this case, mu, it's called the linear density. And it can be found mathematically by dividing the mass of the string or by the length of the string. All right. So the wave travels twice as fast. Now I'm going to make or write these two as equal to each other because they are. So if the speed goes up by 2, twice as fast, that means one of these two has to increase by a factor of 2. And the way to do that is by changing one of these two. We're not changing the tension on the string. In fact, tension is pretty much constant unless you reduce the length or change the mass of the string. We are doing neither for this case. So the speed of the wave is going to be constant. So not A. Tension on the string goes up by a factor of 4. Again, we would have to change either one of these, and we're not doing that. So not that one. The mass per length of the string goes down by a factor of 4. Again, not changing anything here. So nope. The wavelength of the wave goes down by a factor of 2. Now let's look at the wavelength. How long the wave is. You can clearly see that this wave is longer than this wave. By how much? Well, let's see what we did. We increased the frequency by 2 because this has to remain constant. the only thing that can happen is that the length of the wavelength goes down by the same amount, by the factor of 2. So this wave is half of this one. So the answer is D. Now let's just check E. The tension goes up by a factor of 2. Again, we're not changing anything here. Therefore, this is the answer. All right. Last question. If you raise the tension on the string by a factor of 4 while driving it at a fixed frequency, what happens? So let's write down the equation. Okay. So in this case, frequency is fixed, so we are not to touch this one. We are going to increase tension by a factor of 4. Let's use a different color. So then, if I get the square root of 4, I get it is 2. And I get my original equation just with this 2 here. Let me rename these two. So let's call this one lambda prime. I'm not going to rename this one because it's fixed, so it's the same. So then, notice how these two are the same. This has to be the same. So then we can see that the increase here is a 2. And because this is equal to the wave speed, then that means this is equal to twice the speed of the original wave. Why? Because we increase tension by a factor of 2. Just think of an instrument with strength like a guitar. If you tighten the string, it's going to be, your wave is going to travel faster. Normally you get a higher pitch, and that's because you're doing this change here with the tension. So what happens when you quadruple tension of the string? The speed of the wave doubles because the 4 is inside the square root. And that's it.